Okay, so we're going to look at the Trig applications with graphs right now. When last we were together, we looked at finding equations from graphs, and that's going to sort of come into play here as well. But we're going to look at applications of trig graphing. Okay, so we've got applications of trig graphing. Now, there's lots of different scenarios. I talked about the idea that trig graphs, they keep on going. They just repeat the same thing over and over and over and over and over again. So you might think of, well, there's nothing practical like that. But in fact, trig models are used fairly prominently in the real world. And anything that just keeps doing the same thing over and over and over again can be really well modeled with trig equations. And we can use them to predict what's going to happen. So some examples that would make sense to you. The number of hours of daylight in the day versus the time of the year it is. So you think about May 1st. May 1st has, I don't even know, but in the vicinity of, let's say, close to 12 hours of daylight. Whereas if you look in December, it would be down to 8 hours of daylight. Whereas when you look in August, we're up to 15, 16 hours of daylight. And if you kind of graph that through the years, or through the year, you would the winter time with not very much sunlight. As you get into summertime, more sunlight, and then as the fall comes back to the wintertime, and it creates a lovely, better than my diagram there, it creates a lovely sinusoidal function. And so we can actually model the number of hours of sunlight in the day with the sinusoidal function. What else? Well, if you think about tides, if you've ever been to the ocean, you have high tide and you have low tide, and it's extremely predictable. Tides, of course, from the gravitational pull of the moon, and if you look at the depth of the water, versus time, again, low tide goes up to high tide, comes back to low tide, comes up to high tide, and comes up, and on and on and on and on. And what you end up getting is you get a lovely sinusoidal function. Other ones that you might not expect, and some of them are actually pretty cool. If you think about the population, and so I'm going to just do a really quick graph, and you don't have to copy this down by any means. I'm not going to be checking your notebooks, so you don't have to copy anything down. But if we think about, if we had a graph that was time along the bottom, and along this side, I'm going to put number of rabbits. And I'm going to do a graph that you may have never seen before. I'm going to have a second vertical axis, and this vertical axis would have a scale for number of links. Now, there was a dude who kind of sequestered himself in an area of Alaska, actually, where it was really, really prominent, the number of snowshoe hares, and so hares, not rabbits, I guess, and the number of lynx, because lynx prey exclusively almost on rabbit population. So, imagine the rabbit population. There was tons of rabbits, all sorts of them. And what would happen then is the lynx would eat the rabbits, right? Because that's what they do. And as there's a huge number of rabbits, the lynx are going to be successful. So the lynx population is going to increase. So I'm going to go rabbits with black, I guess. And so there's a huge number of rabbits. Lynx propagate. They are very successful. They have litters that all survive. And so the number of rabbits declines. Okay. And it declines and declines and declines. And so the lynx are really, really successful. And they get to a point, though, where, there aren't very many rabbits left. And so, if we then think of the number of lynx, so, I'm going to do lynx. That's also black. I'll go and grab this blue. I think blue. So lynx I'm going to do in blue. So the lynx population was maybe low to start with, but because there were so many rabbits, the lynx population started to increase, right? So the lynx population goes up and 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 up until it gets to an absolute maximum. And there are so many lynx that they're, slaughtering the rabbits pretty successfully. And then what happens is that because of that, there are fewer and fewer rabbits, and so the lynx population starts to decline. And as you can maybe guess, as the lynx population declines, the rabbit population begins to increase, right? And so what you get is this really, really interesting following pattern where the lynx and the rabbits both form a really, really nice sinusoidal set of curves. where one follows along on the other. And it's really neat because it's extremely predictable, barring any unforeseen circumstances. But the lynx curve kind of follows along behind the rabbit curve, and yeah, it's really really neat. So this guy had kind of had game cameras all over the place, and he tracked populations really really carefully, and it was remarkable how successful and how sinusoidal these populations were. So it's really neat. So, he had a sinusoidal model that actually represented this. So we're going to look at some more practical examples, ones that maybe are a little bit more relatable to you. I'm sure that many of you have ridden the Ferris wheel at any number of different venues, like at the Bracebridge Fair or wherever. So imagine I'm going to do my best to draw myself a Ferris wheel. Oh, it's a thing of beauty. Right, so here's my Ferris wheel attached right there. Um, so here's my Ferris wheel. And I'm going to tell you, well, the height of the Ferris wheel, the maximum height of the Ferris wheel at the very, very top is, I don't know, what's reasonable? 30 meters, let's say. Okay, so the very maximum height that you can get to is 30 meters. And you board the Ferris wheel 2 meters above the ground. You have to have like those little stairs, whatever, stairs, and you get on the Ferris wheel. And then the Ferris wheel turns like that. Okay, so what we're going to do is we're going to put Cam. How you doing, Cam? Hope you're doing well. On the Ferris wheel. Whee. Okay, so here's Cam on the Ferris wheel. And the Ferris wheel turns around like that. And it takes exactly 2 minutes per full cycle of the Ferris wheel. Okay, so it doesn't, you might think, well, how is that sinusoidal? It's just going around in a circle, going around in a circle. Well, what we're going to do is we are going to graph Cam's height above the ground versus time for 2 full cycles around the Ferris wheel. Now, this is kind of neat. So I'm going to say this axis is going to be height above the ground. In meters. And this axis is going to be time in minutes. So we're going to assume that we're going to time it from when Cam first gets on the Ferris wheel. Cam, are you wearing a hat? Maybe Cam's wearing a hat. There's his hat. Lovely. Okay, so when he gets on the Ferris wheel, the closest he gets to the ground is 2 meters. And then you think, well, what's the absolute farthest or above the ground that he can get? Well, he gets right to the very top. He's going to be 30 meters above the ground. Ooh. Now, so we know that he's going to start at the bottom, go all the way up to the top, and then come back down, and then go all the way up to the top, and then come back down. One of the measurements that we're going to need is we're going to need to find out exactly what this midpoint is. Now, stop and think about it for a second. Just, in your mind right now, think, that's what the midpoint is. And kind of commit that number, maybe even write it down so that it's somewhere. How many people said 15? Because 15 is not it. It's a really common answer, though. So you're like, oh, half of 30 is 15. That's true, but the base of the Ferris wheel is at 2, not at the ground. So we have to think, oh, from 2 up to 30, what is the midpoint? Well, 30 plus 2 is 32. And then you could add them and divide by 2, and you would say, oh, the midpoint then is 16. That's one way to do it. The other way to do it is to say, well, the Ferris wheel itself is 28 meters in diameter, right? You could think, oh, it's 28 meters because it starts at 2, goes up to 30. Half of 28 is 14, which is true. And so that means that this measurement here is 14 meters. And you add that to the 2, and that's the other way that we can get 16. So a couple ways you can get 16. So the midpoint is 16. And I'm hopeful by now you understand why that's an important measurement. Okay, there's 16. Now, let's think about Cam's motion. You think, well, how's it sinusoidal? Well, here's how it happens. He gets on at 2. As the wheel is turning at a constant speed, And let's assume that Cam is a dedicated ride. He gets to go and not get interrupted for 2 full cycles. When he gets on, at first he's hardly moving up at all. He's only moving up a little bit, right? He's moving more to the side than he is up and down. Over here, he's moving exclusively up and down and not to the side at all. And as he gets to the top, he's not moving up and down nearly as much. He's moving more left and right. So to begin with, he's not getting much higher very quickly. I'm going to grab a different color. So to begin with, he's not getting higher very quickly. He is getting higher, but not very quickly. But then as he gets closer and closer to the midpoint, it starts to get steeper and steeper. But then as he reaches that midpoint and it starts to crest off, it goes like this. Well, what does that look like? Well, that exactly looks like a sinusoidal function. Okay, and then it comes back down smoothly. Ooh, I'm doing pretty well here. Comes down, gets down to the very base of the Ferris wheel's trajectory, and then it curves back up again, goes up and up and up and up and up and up, gets up to the top and slows back down. And then it comes back down, and then it keeps on coming, and that's kind of too steep, but whatever. And here it goes. And you think, hey, that looks really good. I think that looks really good. How long did it take him to go once all the way around? Well, we said right here, it's 2 minutes per full cycle. Full cycle means he started at the bottom, went to the top, and came to the bottom again. So that would represent 2 minutes. And then the second time takes another 2 minutes. So this would be at the 4-minute mark. So what we have is, this is, barring my not all that smooth function, this is a really accurate sinusoidal function of Cam's height above the ground versus time for 2 full cycles of the Ferris wheel. There it is. It's a sinusoidal graph. Lovely. Now, what are we going to do with that? Well, there's lots of things we can do with that. One of the things I'd like you to do is come up with an equation that models the exact pathway of this graph. It's the stuff that we did yesterday. So what I want you to produce, and you should pause the video and do this, is I want you to produce something of the form y equals a times either sine or cos of bx plus c plus d. Now, this is not a super easy one, but it's not too bad. You have definitely the capability if you practiced yesterday. So give this a whirl, pause the video, and come on back. Okay, here we go. So I look at this and I think, what am I going to start with? Well, same thing I started with yesterday, this center line, right? There's my center line. So my center line is the d value. So I'm going to say, I know that this function has a plus 16 hanging off the back. Lovely. And then we think, what is the amplitude? Well, amplitude is how far from the center line we're able to get. So the center line is 16, and I can get all the way down to 2. How far is that? Well, that's 14. So I'm going to come back here and say, all right, this is y equals, I'm going to put a 14. And then, is this sine or cos? Well, sine starts from its midpoint. This starts from its bottom. So it's not sine, got to be cos. Now, I'm going to write that in the center. I know that cosine normally starts at its max. So because this one starts at its min, I know that this one must be negative. Now on to the tougher stuff. So period length. How long is the period length here? Well, I can see that one period took 2 minutes. I know that generally speaking, I find period length by doing 360 divided by b, right? That's what it is. Now, period length here was 2 minutes. So I'm going to come back here and say, the period length is 2. So I'm going to put 2 in for my period length. 2 is equal to 360 over b. And, some of you with the mental math could say, what do I have to divide 360 by to get 2? And you could solve it, which is awesome. Or we could say, I'm going to cross multiply. Multiply up, multiply up. We're going to get 2b is equal to 360 times 1 is 360. Divide by 2, divide by 2. And we're going to get that b is equal to 180, which is weird. Normally 180 was one of the period lengths that we got, but the period length was 2. So we're going to say it's 180x. And then I have to figure out what the c value is. Now, c value describes the left and right, the phase shift. This thing started at 0. Anything that starts at 0, and by start I mean, it's either at the max or the center or the min of its period length or of its amplitude, we're good to go. If it starts from 0, I know that c is also 0. So I don't really need to put the plus 0 there. So I'm just going to rewrite it in this kind of cleaner form. So this has a function of y equals negative 14 cosine of 180x plus 16. And there is the function that describes Cam's height above the ground after x minutes. Okay, we are going to do more with those tomorrow. We're going to look at how we can use those for predictive outcomes. You could say, well, after 95 seconds, how high above the ground is Cam going to be, right? Or you could say, oh, when will Cam be 17.5 meters above the ground? And we can use this equation to do that predicting. That's where these models, that's where modeling things becomes powerful, is that you can figure out, you know, what something is happening in the future or potentially what happened in the past. Okay, so we'll do more with that tomorrow. Today we're going to practice a few more of these application type problems. Okay, so imagine the following. So here we go. So I, being the artist that I am going to take, and we are going to put on a big wheels tricycle. Okay, so you have to envision that what we have here clearly is a big wheels tricycle. Okay, so on our big wheels tricycle, I don't know, we have Hannah. So here's Hannah. Hannah has pigtails today and is riding her big wheels tricycle. Now, the diameter of the front tire of Hannah's big wheel tricycle is 120 centimeters. Okay. Cam, being rather careless, has dropped a piece of gum on the ground, and Hannah has driven over that piece of gum and it has stuck to her tire. Ew, disgusting, Cam. Put your gum in a proper receptacle. However, Hannah doesn't care. She's having too much fun on her tricycle. So Hannah is booking along forwards like this, and the pace she is going at, this piece of gum cycles all the way around every, I don't know, how about we make it every 3 seconds? Hannah's front tire does a complete revolution. Okay, so what I'd like you to do is similar to what we did on that last one. I would like you to go ahead and I would like you to do a exact graph of this scenario, and I would like you to try and do the exact equation that models the height of the gum versus time as Hannah is riding her big wheels tricycle. So give it a whirl, and if you're not there yet, which is fine because we've only just kind of scratched the surface of this, that's fine. You can listen along, but otherwise, you know, pause the video, go off, give it a whirl. But the rest of us, here we go. So I am going to draw in my axes. Now, when it comes to practical real world problems, often we only deal with quadrant 1 because we have positive values and positive values. It doesn't have to be, but that's usually the way it is, and that's why it's called quadrant 1. So I think about the scenario, and I think what is the closest that the gum will get to a height of 0? Well, it's on the ground to start with. So the height is 0 to begin with. And so that would be the bottom of the range of the gum. What is the highest above the ground that the gum is going to get? Well, as Hannah goes forwards, the gum is going to go up till it gets to the top of the tire. So the maximum height the gum is going to reach is 120 centimeters. So the maximum up here is 120 centimeters. So there's the minimum at 0. There is the maximum. So I'm going to label this as height in centimeters. And then what are we going to do? Well, we're going to say I'm going to need my midpoint. Now, this one we can just divide by 2, but it's always good practice to add the lower number and the top number and then divide by 2. So 120 plus 0 is 120. 120 divided by 2 is 60. So the center line is at 60. And then we say, all right, we're going to start with the gum where it is. How long does it take to go all the way around? Well, it tells us right here, every 3 seconds, the gum goes all the way around. So I know one full cycle is going to take 3 seconds. So a second full cycle is going to take me out to 6 seconds. And I'm going to label this with time in seconds. Now, the gum starts on the ground, goes all the way to the top, and then comes back down. Goes all the way to the ground, all the way to the top, and then all the way back down. So I'm going to go ahead and I'm going to sketch that in. Okay, so here we go. Ooh, I didn't actually select the other color. Oh, well. Comes back down, goes all the way to the top, comes all the way back down. And there we go. There are our 2 full cycles of the bubble gum on Hannah's tire. Okay, lovely. Now, what we're going to have to do is I want you to, if you haven't already done so, to find the equation. So some of you maybe we're going to struggle with the graph. You should be able to get to the equation because that's what we've been doing for the last 2 days. Pause the video now if you haven't already and get the equation. Otherwise, here we go. So I'm going to write the general form. The general form is y equals a of sine or cos of bx plus c plus d. Okay. Now, d is always the easy one. It's going to be 60. Okay, so I know that there's a plus 60 hanging off the back here. Plus 60, because that's the center line. There it is right there, center line. And then amplitude, how far from the center line we can get. Well, center line, you can get all the way to 0. So the distance is 60. So not only is the center line 60, but the amplitude is 60 as well. So I know that this is 60. And it starts at its minimum, not its center. So I know that it's going to be cos. And because it starts at its minimum, I know that not only is it cos, it is a negative cos. So I need to put the negative in there. Now, it's got a period length of 3. So I know that equation is period length is equal to 360 divided by b. But in this case, the period length is 3. So 3 is going to go there. And I'm going to say 360 over b. Some of you can probably do this in your head, figure out what that value is. For those of you who can't, we're going to cross multiply. And we're going to say that 3b is equal to 360 times 1 is 360. Divide by 3, divide by 3. And we're going to get that b is equal to 120. So we're going to come back here and we're going to say, all right, it's 120x. And then we have to think about what the c value is right there. Man, the 60 should be over here. Nevertheless, the c value is how much there is of a phase shift. Now, good practice would be to say, okay, the phase shift is 0, so we can figure out that it's 0. Here's a little pro tip for you. I am not going to give you an application problem that ever involves this c value. It's always good practice to think about it, but for practical purposes in this course, I am not going to give you a c value for application problems. I might, just like we did yesterday, with just a graph and you have to figure it out, but for application problems, I'm not going to. So that means that the gum equation for Hannah is y equals negative 60 cosine of 120x plus 60. Okay, there you go. So we're going to do one more as practice, and that will be that. And so here we go. So imagine the following. We have a retaining wall on a waterfront property on the ocean, okay? And the retaining wall, the tide moves up and down the retaining wall. And so we are going to call, this is going to be ground level is going to be 0. High tide, it's negative 1 meters above the ground. Low tide, it is negative 9 meters. These are pretty huge tides. They're 8-meter tides. Where do we have the highest tides in the world? That's right, the Bay of Fundy. So this is going to be a retaining wall on the Bay of Fundy. So at low tide, the water is 9 meters below ground level. And at high tide, it is -1, so 1 meter below ground level. It takes from low tide to high tide takes 6 hours. So that means to go from low tide to high tide takes 6 hours. And similarly, from high to low is another 6 hours. Okay. What I'd like you to do is I would like you to come up with a graph, and the graph is going to have from the height of the water below ground level versus time for 2 full cycles. I'd like you to graph it. And then what I'd like you to do is I would like you to come up with an equation that models this scenario. Okay, give it a whirl. Okay, so here we go. This one's going to be a little bit tougher. That is not a straight line. There is a straight line. Now, here's what we're going to do. This time, we're actually into quadrant. There's 1, 2, 3, 4. This is quadrant 4. And I'm going to label them off. The high point that the water gets to is -1. The low point that the water gets to is -9. That means that the center point, because we need that, how are we going to do it? Well, there's a couple different ways, but the easy way is to say -1 plus -9 is -10. -10 divided by 2 is -5. So there's my center line. Now, I guess I didn't actually stipulate it. This is, starting from low tide. So my apologies if you're like, well, how do I even know? This is going to be starting from low tide. So this is height in meters again. And this axis along the top here is going to be time in hours. Now, I'll admit I was tricky with this one. How long does one full cycle take? Kind of the 6 jumps out at us, but a full cycle is for it to fully repeat. That means it needs to go from low tide to high tide back to low tide. So the period length isn't 6, the period length is, of course, 12 hours. And so that means for 2 full cycles, it's going to take me out to 24 hours. Okay, so we're going to start at low tide, and we're going to go and then go, and there it is. Okay, so I'm going to go ahead and I'm going to sketch that in as best I can, which is not very well. Up we go, hit the top that we're allowed to get to, come back down, get to low tide, tide turns around, comes back again, reaches the top, comes back down, and there we go. And so there is a graph that represents the depth of the tide versus time. Awesome. Now we need an equation. So if you haven't done it, pause the video, please, because you really should try these and get good at these and get me an equation. I'm going to go ahead and I'm going to write the general form. So y equals a sine or cos of bx plus c. And I know that we're not going to use the c, but I'm still going to put it there because it's part of the general form, plus d. Let's knock out the things in order. We know that the center line is -5. So we're going to need a -5 hanging off the back. And then we can see what is the amplitude. From the center line to either the max or the min is a distance of 4. So I know that it's going to be 4. Now, it starts at the bottom, so it's not sine, which means it has to be cos. And I'm going to just make myself some room here. I didn't really leave myself proper room. What's going on? Why didn't I get that? It is the hard eraser. Why are you not hard erasing? I don't know, whatever. So I know that because it starts at the bottom, it's going to have to be negative cos. Now, this has a period length of 12. Okay, so I know the equation is period length is equal to 360 over b. But in this case, period length is 12. So I'm going to come and I'm going to put the 12 in for period length. I'm going to say that's 360 over b. I'm going to cross multiply, and we're going to get that 12b equals 360. Divide both sides by 12, divide by 12, and we're going to find that b is equal to, drop that into your calculator, And I think that we're going to find out that that is not degrees, just 30. So I'm going to come back here and say, all right, that's going to be 30 and x, because I know there is no c, it starts at 0. So there is the equation. Y equals -4 cosine of 30x minus 5. Okay, I'm going to go ahead and I'm going to stop the video, but I'm going to draw out another scenario that I would like you to go ahead and do this same exercise. Tomorrow, what we're going to do is we're going to look at using these equations that we come up with to do some predictive and some actual calculations of real world effects. Okay, thank you.